Okay, in question 1 then, this is our situation. We've got light coming in from the air, coming into the glass cube and getting refracted, so that angle changes, and then arriving at this wall, and basically the question is what happens after that. So the first thing to take on board is this piece of information, that the critical angle is 45 degrees. What that means is that if the angle between the normal remember is the direction that's at right angles to the plane that it's hitting, and if that angle from the normal to your ray is greater than 45 degrees, it means that there will be no refracted ray emerging on the other side, and instead you'll get total internal reflection. Okay, so the critical angle is a very important thing because it tells you whether you're going to get some light emerging out the other side or whether it's all going to bounce back inside, and it basically just depends on where you are relative to the critical angle. So in this case, 50 degrees is bigger than the critical angle. That means no refraction. All of the light is going to be reflected. So we're going to get this situation where that angle is 50 degrees, matching this one. Okay, so then if we think about the other angles in here, you can see that because this is a right angle triangle here, because you're in a cube there, if this angle is 50 degrees, this one is 40 degrees, and if this one's 40 degrees, then this one is 50 degrees. Okay, because that's must be the case in order that the angles in the triangle add up to 180 degrees. So we can see that the angle relative to the normal of that light here is 40 degrees in there. Okay, so now if we look at this triangle at the bottom here, again you can see if that's 50 degrees, then this is 40 degrees, and if that's 40 degrees, then this is 50 degrees. So if we now put our normal on here, like that, again perpendicular to the plane that it's hitting, you can see that that angle must be 40 degrees. Okay, because 50 plus 40 will equal 90. So this ray is coming in at an angle of 40 degrees to the normal as the light passes between the denser and the less optically dense medium. And you can see that's exactly the same situation as up here. The direction of the light is going here from air into glass and there from glass into air, but you can see the angles are the same. Okay, so it's 40 degrees from the normal there within the glass as it is there, and that means when it emerges into the air, it will be theta degrees from the normal up down here, just as it was up there. So we can therefore draw this emerging ray like that. Sorry, that's horrible. Try that. See if we get something a bit closer to a straight line this time. So you're going to get something like that, where this angle is going to be theta. Okay, because it's just the same situation as we had up there. Okay, so those are the important things, to get the total internal reflection there, so that you get those two 50-degree angles, and then realizing that what happens here is basically the same as what happens there. Part B is relatively straightforward once you're familiar with the ideas about refractive index and critical angle, which are summarized on the datasheet. So it gives you three important bits of information about refractive index there, which you need to be able to use. So the first is the definition here, that refractive index n is equal to the ratio of the speed of light in a vacuum, which is c, divided by the speed of light when it's passing through that medium. And that's always going to be lower, because the idea is that the interaction between the light waves and the particles that it's kind of passing through slows it down. We really can't get into the detail of that. That's really quite a tricky sort of quantum mechanical thing, but the upshot of it is important, that the speed of light in some kind of medium is always going to be less than the speed of light in a vacuum, and therefore that ratio must be bigger than 1. And if you have a medium which has very few particles in it, like air, then actually it won't be very different from 1, because the interaction with the occasional particle that the light happens to encounter will have, an almost negligible effect. Okay, but it's approximately equal to 1 for low density media like air. And so for our purposes we treat it as being equal to 1 in those situations. So that's important that you remember this bit, because the definition is there on the data sheet, but you do need to know, in effect, that CS, the speed of light within a substance, has got to be bigger than 1. But you also need to know that if one of the substances you're dealing with is air, then you can treat the refractive index of that substance as being equal to 1. So the second thing is Snell's law, which the datasheet calls the law of refraction, which is this. And again, you don't have to know how to derive that, but it's a hugely important law because it lets you calculate what the path of light will be as it moves between media. So that will be true regardless of whether N1 is bigger than N2 or smaller than N2. That expression will always be correct. But the one we need to solve for the critical angle is the third one, which is given to you there. We could actually derive that from here, and it's probably worth pausing to do that, but it's also important to remember that it's on there, so you don't actually have to do the full derivation every time you have to calculate a critical angle. So let's just have a look at how that works. So suppose we have glass here, or whatever the medium might be, some crystal or plastic, whatever it might be of some kind, and we've got air on the other side. So if this is the normal, okay, so perpendicular to the interface plane, then what's going to happen is that as the light comes in at some angle theta, like that, and we'll call that θ1, the angle in the glass. And I've chosen to do it that way round so that we can derive this derivation, because remember, glass is going to have a higher refractive index than the air, so we'll call that one θ1. And what we know is that because N1 is bigger for the glass, sine theta is going to be smaller, and therefore theta is going to be smaller for the glass. In other words, the ray is going to be closer to the normal in the glass than in the air, so when it moves out to here, we're going to get θ2, which is going to be a bigger angle. Now let's think about what happens as we increase the value of θ1. Okay, so let's go to here and say, right, here's a bigger angle, θ1, and you can see again from this that if sine θ1 is bigger, then sine θ2 has to be bigger in the same proportion, because N1 and N2 are still what they are. So if we increase the value of θ1, we'll have to increase the value of θ2 as well, like that. But you can see what's going to happen eventually, and I've run out of colours now, so I'll just do it here with a dotted line. We're going to get a ray coming in like this, where this is now our biggest value of θ1, which we're going to call θc, the critical angle. And what makes it critical is that when the light is diffracted, it's actually diffracted through 90. Try that again. What makes it critical is that when the light is refracted, it's now bent so that this angle becomes 90 degrees from the normal. And obviously that's as far as it can go, so that's the limit of when you can of where you can get refraction happening. So any angle θ1 bigger than that, there isn't going to be any refraction, and that's when you get total internal reflection. So if we use this relationship here, we've got n1 sine θ1 is equal to n2 sine θ2. But remember that medium 2 is the air, so n2 is equal to 1 because it's air. So we've got that n1 sine 1 is equal to sine θ2. And if we're at the critical angle, then we have n1 sine θ critical is equal to the sine of 90 degrees, which is equal to 1. Okay, because if the ray's been refracted all the way to there, then it's 90 degrees from the normal. So sine θ2 is sine of 90 degrees, which is equal to 1. So therefore sine of θc is equal to 1 over n1, which is basically this statement. This is a more general thing because this is allowing for n1 and n2, it's allowing for the situation where neither of those is air or anything approximating to a vacuum, so that you would then get values for both of these things. But in our particular case, in part B, n2 is equal to 1 because medium 2 is the air. So sine θc is equal to 1 over n1, which we can therefore rearrange to get that n1 is equal to 1 over sine θc, which is 1 over sine of 45 degrees, which is indeed 1.41, which is what it says in the question. Okay, so you could get the answer just by doing that, and in fact you could get the answer just from here. Okay, so you don't need to do the derivation to get there. You could get the answer just from this bit and just say, right, because medium 2 is the air, n2 is 1, so sine θ is 1 over n1, and therefore it's trivial. But this little bit of background is quite useful. But don't go rediscovering the wheel in an exam. Remember that bit of information is there. Coming on to part C, we already worked out in the first part of the question that because this angle it gives you in the question is 50 degrees, then that angle must also be 50 degrees C, sorry, 50 degrees C, 50 degrees, and therefore the angle that we're interested in terms of the question is theta there. So what can we do with that? Well, what we know is that this angle must be 40 degrees, because obviously those two angles add up to 90, because that's the right angle. So that's the angle between the refracted ray and the normal. And then we can use the law of refraction, which is that n1 sine θ1 is equal to n2 sine θ2. So within this medium we've got that 1.41, because remember this is the glass and the refractive index we've worked out is 1.41, sine of 40 degrees. Okay, so that's the refractive index of the glass that we worked out from B, times sine of that angle, because that's the angle between the refracted ray and the normal, is equal to N2, which is 1, times sine theta 2, which is just theta. And it's as simple as that. So we can therefore just simply say, because let's just annotate that to make sure that that's refractive index of air, which is very close to 1. So alright, it's approximately equal to 1, but it really is very close, so it's not a dodgy approximation. So all we got to do is to find that, therefore, that sine theta 2, or sine theta, which is what theta 2 is equal to 1.41 times sine 40 degrees, which is 0.906. And therefore theta is just the inverse sine of that, which comes out to be 65 degrees C. 65 degrees, not 65 degrees C, 65 degrees from the normal. Okay, so it's straightforwardly a case of getting that from your data sheet, remembering that N2 is 1 because it's air, and realising that you'd worked that out from the, well, both these things out in earlier parts of the question. Okay, so part C is then asking us about an optical fibre, so it gives you this sketch of an optical fibre which looks a little bit like that, and then we've got this ray coming in there incident on the end of the fibre like that. So at this interface we're going to get refraction, because obviously the fibre is going to be made out of some kind of plastic or glass material, and so it's going to have a higher refractive index than the air that the incident ray is travelling through. So if we put the normal on here, okay, perpendicular, that's not very good, normal, okay, so perpendicular to the plane at the end there. If you're moving into a medium of higher refractive index, remember the law of refraction tells you that you're going to now move closer to the normal. So what's going to happen is that you're going to get bending here, and the light's going to move closer to the normal there. So you're going to get something like that. Okay, so the light is refracted there. Now, for the light to propagate through the optical fibre, you have to get total internal reflection there. If you don't get total internal reflection, you're going to get lots of loss of your light just through passing through the cladding to the outside. So the total internal reflection off the walls is the key thing, and that's what the path is next going to depend on. So total internal reflection means that that angle, the angle of incidence, equals the angle it bounces off at, the angle of reflection. So you just need to draw something that makes it look as if that's essentially true, which is going to look something like that. Okay, so that's the pathway, okay, with total internal reflection there. And then the same situation here, where that angle, oops, means that this is going to come out something like that. Okay, so it's this total internal reflection off the walls that allows the ray to pass through the optical fibre, and then when it gets to the end, it's going to be refracted again. So again, if we draw the normal on there, because this time it's passing into a medium of lower refractive index, which is back into the air, then the refracted ray is going to be further away from the normal. So you're going to have that kind of bending. So it's the opposite of what went on there. And so that's the emergent ray coming out at the end there. So part 2 is asking us to just name this process that happens at the end. So no trick there, that's simply refraction is all that it's looking for, the change in the angle relative to the normal as it passes between these media with different refractive indices. And then part 3, we have again a critical angle calculation. So let's go straight to the data sheet this time and write down this statement, which is where we're going to start, that the sine of the critical angle is equal to n2 over n1, where n1 is obviously got to be greater than n2, otherwise that doesn't give a meaningful answer because you can't have a sine bigger than 1. Okay, so in this instance it tells us that we've got the cladding with a refractive index of 1.45. So this is the cladding. And then we've got the fibre with a refractive index of 1.50. Okay, so we can therefore say that sine of the critical angle is equal to 1.45 divided by 1.50, which is equal to 0.9667, and therefore the critical angle is just sine to the minus 1 of 0.9667, which works out as 75.2 degrees is the critical angle. Okay, so part 3 explores this idea of what is the critical angle in the optical fibre. So remember that what happens is, if this is your normal, the light's passing through the core, and what we don't want it to do is to escape out into the cladding. And so provided that this angle theta there is big enough, we'll get total internal reflection, and this will come back here, which is what we want. But if we hit it at too acute an angle, then if that's below the critical angle, this value here, then the problem is that we won't get total internal reflection, and we'll get some escaping out into the lower optical density cladding like that, and that's what we need to avoid. So the critical angle is very important for the functioning of optical fibres. So here we've got to do the calculation, and it gives us these numbers. So the key thing is to use this relationship which is on your data sheet, which is that the sine of the critical angle is equal to n1, sorry, let's get this the right way around, n2 over n1 is what it says, where obviously n1 has to be bigger than n2, otherwise that would come out bigger than 1 and it wouldn't make sense. So you can always tell which way around that has to be. And we just literally got to put the numbers in. So the sine of the critical angle is therefore equal to 1.45 divided by 1.50, which is 0.967, and therefore theta is just the inverse sine of 0.967, which is 75.2 degrees is the answer. So then it wants to know a reason why cladding is used in optical fibres. Actually, the simplest reason you could give, which would be acceptable, would simply to say that it's physically to protect the core of the fibre from damage, and that would be true. The other sort of slightly more interesting reason is that normally optical fibres are used in bundles so that you'll have lots of them sort of running parallel with one another. And you can see that the cores mustn't touch, because the total internal reflection depends on the light getting to here and then encountering a medium with a smaller refractive index. And obviously if the cores were touching one another, it would be touching a medium with the same refractive index, and the light could just keep on going. So the light would escape from the core into an adjacent core if they were in direct contact. So you can say that a function of the cladding is to make sure you have internal reflection by providing a medium of lower optical density surrounding the core and preventing adjacent cores from touching. And then following on from that, it says, well, why might it be good to have a medium with a lower refractive index than 1.45? And what we've said is that you can actually see the answer from this relationship, that the sine of the critical angle is n2 over n1, and you can see that if n2, which is the refractive index of the material on the outside, if n2 is smaller, then sine theta, sine of the critical angle, will be smaller, and therefore theta will be smaller. And what that will mean is that, you know, if your original critical angle was that, it would mean that any light coming in, you know, at these kind of angles, coming up to that point, would escape. And so you would then lose light unless you were sure that it was coming in at really quite a big angle theta. You can see we got 75 degrees there. So only light with in this area really with a bigger angle than 75 degrees would get totally internally reflected. If you make this number smaller, then theta is smaller, and so that would mean that anything in that area would be totally internally reflected, and therefore you would get a bigger range of angles through which you could still get transmission of light through the cable. So that's the answer. Basically, you just have to say a smaller critical angle, and therefore there's less risk of light being lost by being refracted out of the core rather than being totally internally reflected. And finally, part C wants uses of optical fibres. The big one is transmission of data. So, you know, phone lines and stuff like that is a huge application. Another one which is more specialised but which is very important that you might mention is endoscopy, which is a medical process where you can use an optical fibre to basically obtain images from inside the body. So for example, if you want to get images from within the digestive system, you can either stick an optical fibre down your throat or stick it up from the other end and basically shine light through it and get an image through the optical fibre.